Well, let's get into this. I was going to do black holes today, but then I thought about it. It's really better done next week. We didn't finish properly the origins of life last time, and that's very important to cover. So I thought that that's what we would do today, and maybe take a step forward too. Well, you saw this slide last week, and it's a stellar a nursery, if you like, for stars. But this would be maybe 13 point, I don't know, 2-3 billion years ago. Certainly after the first generation of stars have been created, but because this is seen through an infrared lens, so you can actually see these kind of amorphous, kind of gaseous clouds, and those gaseous clouds are just absolutely jam-packed with hydrogen and, to a lesser extent, helium. It's about 75% to 25%, and a tiny, tiny little bit of lithium. And then here are the stars. But in earlier times, when we only had visible light to deal with, none of this stuff, none of these kind of gaseous clouds were visible. So, and here's that wavelength thing. Here's the bandwidth from the radio wave. Now they would continue out here, ever lengthening here, and shorter here. By the way, different shorter and shorter frequencies become more and more energetic. And so it's not surprising that gamma rays can be dangerous forces, all right? And but here's the visible light band, the kind of red moving into the infrared and beyond into the microwave. Remember I talked about the background radiation, that pattern, that trace was left over that began about 400,000 years after the Big Bang, and light was finally able to escape this highly energetic ionized universe, which had cooled down a lot, and light was able to escape, and it may have been visible light then, but now it's in the microwave range, so that's what's detected now as the evidence of that really old light signal that was released about 400,000 years after the Big Bang. I showed you this the last time, but I want to repeat it because we're going to talk about these number games. So based on a conservative estimate, and this is a very conservative estimate. I mean, this was a large committee of astrophysicists and people in the know of this kind of stuff who said, okay, what are reasonable criteria for a habitable planet? And it turns out that in the Milky Way, there are around 300 million stars with planets that might support life in some fashion. Well, you don't have to be much of a mathematician to realize that at a minimum, there are a trillion galaxies, or maybe 2 or 3, within the visible universe that you can see. The limits of the universe we actually can't see yet. So it may be much larger than we think. So there could be many, many more, but at a conservative estimate, 1 trillion galaxies, just multiply one by the other. And when you get up to 10 to the 19th, that's a lot of potentially habitable planets. So even if you're really conservative and say, gee, only 1 in a trillion, let's make the odds really bad. There's still a lot of habitable planets around in the universe. Now, most of them are well beyond our reach to ever get to or ever receive a signal from. But the other thing is, there are a lot of red dwarf stars. They actually outnumber bright stars. These are cooler stars, hence the red. And some of them have planets orbiting much closer to them to be in the habitable zone. And they're more common than the brighter stars that we talk about. So if you add them in, the numbers go up again. So is the chance of life high? I think it is. Now, so far, the number of exoplanets actually identified is somewhere number, several thousand. But remember, they're only looking in a small corner of the Milky Way close to us in the Milky Way. This is not a 2,000 or 3,000 or 8,000 or 10,000 found in the Milky Way. It's in one small corner of the Milky Way, one spiral arm of the Milky Way, and not all of that spiral arm. So I think, is it likely? Is it probable? I think it's certain, actually. Well, back to Andrew Noel. Now, this is a scientist's way of thinking about life. Maybe not something that you and I would come up with, but for them, it's very important. It's something that they have to think about with Mars and other bodies where you're looking for life. Or what is in fact, your definition of life? Well, what is life anyway? So I'm quoting him, what differentiates us and dogs and oak trees and bacteria from mountains, volcanoes, and minerals. On the strength of our own lives or those of our children, we might volunteer that organisms grow. Well, true, but so do crystals. But organisms not only grow, but reproduce, making more of themselves through time. Organisms harvest energy required for growth and reproduction from their environments. Welcome. A set of processes that biologists call metabolism. Now, this has an importance in the next one or two slides. And critically, life evolves. Crystals, on the other hand, grow only by adding more of the same, but none evolve into something else. Only life evolves into something else. That's a very broad definition of life, but it's very solid, and it's the kind of stuff that NASA can use for what life is when they're looking for it. When rovers getting around drilling holes and that kind of thing, this is the kind of working definition that they're using. So, well, you've seen this slide. By the way, I don't have those one saying I didn't just need the 13 used to go over here, but it's very striking. Composition of the Earth and the cells in the human body. Isn't it really striking that the composition of the Earth, that well over 95% of it is just four elements: iron in the core, oxygen, silicon, the mantle, magnesium. That's really impressive, and it's very, very different than us. Now, both of us, oxygen 31% here, 65% in our body, but where's the carbon, hydrogen, nitrogen, calcium, phosphorus, and all the other life elements in? We're well under the kind of 0.01%, the composition of the Earth. So it may be dust to dust, but we're talking about a different kind of dust, aren't we? Now let's just move along. Oh, what happened? Hate it when a thing freezes like that. Oh, it's catching up, I think. So wait and see. What happened there? Oh, that's interesting. Oh, here we go. So here's the we saw this last week, maybe even the week before that. Oh, here we are, back and go. Must have taken a long time. Well, we can work with this. Anyway, here we are, the elements of, oh, give it a little time now. I hate this. Anyway, here they are. So elements of life: hydrogen, made in the Big Bang, and helium and lithium. They're made in the Big Bang. But sodium, magnesium, potassium, calcium, iron, carbon, nitrogen, oxygen, phosphorus, and sulfur, those are the key elements of life. And so we're going to be talking about them a little bit more as we move along. See? Wow. What's going on here? Oh, well, maybe here we are. Interstellar space and carbon-based molecules. Now, this trouble before. Okay, interstellar space and carbon-based, I talked about this last week, these gigantic clouds and otherwise dark space of hydrogen, helium, and the stellar remnants of supernovae, including carbon, the elements of life, carbon, oxygen, nitrogen, phosphorus, sulfur, and sodium, potassium, chloride, and calcium, etc. But anyway, there are vast clouds containing these. But there are also clouds of simple carbon-based molecules that link carbon to oxygen or hydrogen. They're really very common. These are huge clouds. Now, these are just a few, in both cases. These clouds are maybe a few degrees above absolute zero. And even though the elements in the compounds are widely dispersed from each other, there's a huge number of them simply because of the vastness of space. And sometimes, in the case of these carbon-based, very simple molecules here, just random chance. And sometimes they strike one another and form a slightly more complex molecule. And some of them probably seed plants, including Earth. So some components of life probably are a product of kind of seeding the planet from space. Now let's move on. Here we are. Now, I love this slide. The more I look at this, the more I like it. It looks busy, I know. It's DNA. You've seen this a lot. It's the double helix. Think about it. Just pull it out straight and untwist it, and you've got a ladder. And on the outside of the ladder are these phosphate groups and sugar groups, and they're very repetitious. Phosphate, sugar, phosphate, sugar, phosphate, sugar, phosphate, sugar. So that's the side of the ladder on both sides. So that provides the rigidity to the skeletal framework for the DNA. The bases that provide the bases of our genes are in the middle. And they're in pairs, thymine with adenine and cytosine with guanine. Now just look a little carefully here. Notice that one basic type involves one carbon ring. The other, so thymine has one carbon ring. Adenine has two carbon rings. Guanidine has two carbon rings. Cytosine has one carbon ring. So they run to a pattern, don't they? And this was the great insight that Watson apparently had, because when they were trying to figure out the structure of DNA, the rung of the ladder had to be the same length. And the only way he could figure that out was pairing them in this way: a double carbon skeleton here with a single. So wherever you had a double carbon one, it would match with a single one, and would provide the same distance between the two sides of the ladder. That's really important. And then look at the elements. I mean, they are the elements of life, right? Here's hydrogen from the Big Bang. Nitrogen here. There's a lot of carbon in these rings here. And over here, kind of the phosphate over here. So these are the elements of life. It's really very incredibly simple, looked at this way. Sometimes, I'll get onto this a little bit later, but sometimes I think chemists have been a disservice to us because they use kind of funny words. They create a kind of a language problem for us in explaining it to others or teaching others, and they make subjects unnecessarily complex for us to understand. So that's DNA. Now, there have been two major experiments in creating life molecules. One of them, the most famous, is Stanley Miller's and Harold Urey back in 1953. And they started out, okay, what was the early in Earth's history, what was the atmosphere like, and can we simulate that in the lab, and can we produce organic life molecules? And I don't know whether you've seen pictures of the experiment, but it was really pretty simple. But it combined water vapor, carbon dioxide, so they thought the atmosphere would contain a lot of carbon dioxide and methane and ammonia. It turned out to be wrong. It's not their fault. And electrical discharges, meaning lightning. To simulate lightning, electrical discharges, and they were able to create several amino acids. Well, that got a lot of people excited. If you could, with relatively simple experiments on Earth, produce in the lab at least some molecules of life, such as in this case, amino acids, because amino acids make proteins. You string them together to get proteins. Half a century later, John, so this is still quoted because of its importance. It's the first time somebody tried to create life molecules artificially in the lab. Now, of course, they're creating DNA with different artificial bases and changing the phosphate group and seeing what they can get away with by actually changing the molecule of life. I'm not sure that's a good thing to be doing. Half a century later, not so long ago, John Sutherland and his colleagues managed to create two nucleotides. Remember the base and the sugar and the phosphate. Those three together form a nucleotide. And they managed to create two of them. But that's about as far as it went. Now, here's where the rub is. If you look for the fingerprints of earliest life, what do you look for? Well, most people in the past have looked for something that looks like a simple cells, meaning like a bacteria or an archaea. And these are two families, basic families of life, bacteria, archaea, and they look the same under a microscope. They possess RNA and sometimes DNA, but the problem is they're anything but simple. They're actually very well evolved. They've got a cell membrane, they've got a whole apparatus for making energy. They can create hundreds of thousands of proteins. They can create hundreds of thousands of genes. So they're actually highly evolved, although they look very simple, they're anything but. So this begs the question, well, how did they get to there? And how did that happen? Well, frankly, we don't have a clue. But moving forward, at around the 2 billion mark, archaea, somewhere, maybe many times, engulfed bacteria. And kind of strip the bacteria in the process of everything except the energy mechanism in the bacteria. And mammalian cells, or animal cells, that became mitochondria. And we have, if you look at any human cell, whether it's a nerve cell or a white blood cell, they've got hundreds of these mitochondria there visibly making energy for us. And if in plants, this very similar kind of factory for energy, these chloroplasts. Both of them provide a high energy source for these more complex, now nucleated cells. These cells look more complex under the microscope because there is a nucleus. The DNA or RNA, or both are within an enclosing membrane. And they have other differentiated membrane-bound organelles in the cytoplasm, so they look more complex. Those eukaryotic cells, those more complex cells, developed into simple multicellular organisms. Now, initially, it was just kind of a congregation of these cells, kind of living together in a commune, so to speak, but no more attachment than that. And then they differentiated. Some of them became specialized to do this job, and other jobs. So now you get an increasingly complex, integrated biological system of cells, with some of them having very different jobs than other cells, much like we have brain cells, and even among the brain cells, maybe as 200 different subtypes, at least under the microscope. And all kinds of, with the COVID, we realized that there are all kinds of, in my anyway, that there are all kinds of specialized cells that are bone marrow and lymph nodes that are part of the lymphatic system and our immune system, highly differentiated from one another, highly specialized. And that's the way it's become. The big event in life, if you think about the Earth being around for, say, 4.5 billion years, if this were a 10-chapter book, the last chapter, chapter 10, is when all the real action that we would associate with life took place, meaning complex, multicellular organisms, animals, trees, all those kinds of complex life forms. That's only in the last half a billion years. It's really extraordinary. And to kind of summarize this, so Earth's origin. So this is all about perspective. This whole series is about telling stories, but it's also about perspective. And Earth's origin go back to 4.5 billion years. Earliest microbial life, maybe half a billion years later. This great oxygenation period when the atmosphere acquired a lot of oxygen, around 2.3 billion years ago, and kind of corresponded to the development of these complex eukaryotic cells. The Cambrian one, around half a billion years ago, the common ancestor for us and the chimpanzees and later bonobos, 5 to 6 million years ago. So the big picture is that's what it is. Well, then the question, there are a lot of questions. I mean, I don't know when they're going to sort this out, but it won't be in my lifetime. Where was the first life created? Well, Charles Darwin speculated. He was a very conservative person. He would have been somebody I think we would have liked to know. He was he's a curious person, interesting stuff, good observer of Mother Nature around him. I mean, he actually did a study, wrote a book on worms in 1 acre of his land. And the number of worms actually arrived at some count of the number of earthworms in this 1 acre of land that he owned. Anyway, in these worm soup ponds, as Charles Darwin imagined, very unlikely. Deep sea vents near volcanic eruptions, that's William Martin's favorite, and he may be right. Hot springs. You know, life is incredibly durable. If you've been to Yellowstone and you see the hot springs, there is life in that stuff where there's stuff bubbling up. And water is close to the boiling point, in some places exceeding the boiling point. And life, in some forms, survives. It survives a mile down or 2 miles down in deep mines. It survives up in the upper atmosphere. It survives in frozen areas. Life finds a way extraordinarily. It adapts. And there's one of those vents. Why are the vents so interesting? Because they're a huge source of, they're a mineral or element-rich source. Usually it's where 2 crusts have come together and create, they're either overriding or undercutting one another, and some of them create volcanoes. But the important thing with all that kind of disruption taking place, it's a mineral, element-rich environment. It's also an energy-rich environment. So it's a great place, if life is going to take place, it's a very good place to go looking. And now, then the big mystery, well, which molecules came first? I mean, if you look at a complex cell and you look at it, you say, gee, in what order did that develop? What came first? Was it RNA? Certainly not DNA. DNA is twice as complex. But was it RNA came first, or some version of proteins, or something else? Well, what are those options? RNA is a very attractive one. Probably the majority of people like the RNA hypothesis. Why? Because even simple, short strands of RNA are capable of replicating. They're also capable of assembling short several amino acids into simple proteins. And they can make copies of themselves. Isn't that what we would be interested in? So that's why the interest in RNA. And then at some point in evolution, those two strands kind of came together. Or two strands came together that had DNA. So that kind of makes sense in a way. The other thing that as Noel points out, it's possible to generate RNA which contains bases and sugars and phosphate groups from substances that are readily available on Earth, hydrogen cyanide and formaldehyde, or the weathering of rocks. So in other words, these building blocks of nucleotides are actually common, geologically speaking. So it wouldn't be any surprise for them to kind of self-assemble somewhere and create the molecules of life. Another one that's gaining traction is a very interesting one. Krebs got a Nobel Prize back in the 1920s for working out a metabolic cycle. I can tell you that if you went to any chemistry lab around the world, somewhere on a wall there would be a great big sheet showing this, the Krebs cycle, without this outside stuff, but they would show this whole cycle. And Rita would know Susan Hall, and Susan Hall became an expert and memorized all of this kind of stuff when she did her PhD in Ottawa years ago. But it's one of those. But if look at this, they've actually got the carbon atoms here and the oxygen atoms. And if you look a little closely, never mind what they're being called here, citrate and etc. around here, the various names you go around here. Just look, there's very little change. There's these inner collection of this kind of group of 4 carbons here repeats right up to the end here. And all that's happening, step by step, is rearranging some of the oxygen atoms and sometimes knocking off a carbon or two, or knocking off an oxygen or two, but we're talking about 2 atoms here in the basic molecule. So it's intimidating to look at the English or Latin names for all this stuff, but if you look at the basic chemistry, it's actually fairly simple, or a lot more simple than you think. But the end product is high energy phosphate. So people looked at this and they thought, well, hey, this is a low energy pathway, meaning there isn't a lot of energy required for each of these equations to kind of take place around here, or each of these reactions to take place around here. So if the train runs in one direction, could it run in the other direction and reverse? Well, it can. And if you take this pathway, and a simpler one at that, the kind that might have been around early, you can actually make amino acids, bases, sugar groups, phosphate groups, and all of the molecules of life. Isn't that extraordinary? There's just one metabolic pathway. So maybe this metabolic pathway, this intimidatingly complex pathway, was much simpler at one time. And it was possible to run it backwards and create those molecules of life. It's a very interesting hypothesis. Well, the big question remains, how did the simplest of cells develop and how did they become so complex? So after how long we've been talking. So half an hour, I can say we don't know. But Winston Churchill had his ideas. I'm going to go over this a bit. I mentioned it before, but an extraordinary fellow. I mean, he wasn't the first male in the family, so he didn't have much money, if any. So he had to earn his own keep through his life.
I tried to get this article that you mentioned before, and it said it was copyrighted, and they wouldn't produce it. There's a press of what he said, but you couldn't get the original from my email. Anyhow, from my
I can probably got the original. Might be able to get it for you. I asked the journal Nature if it's okay to use it, and that's why I stuck that on there. But the important thing is this guy is a creative guy. You know, his best friend is a scientist, this Lindemann fellow. That's his best friend in the 1930s and through the period of the war and after. He's very sympathetic to the science community. He's the first one to support a scientist in the cabinet. And he doesn't have cabinet meetings with everyone around, kind of 30 in a room. He meets with people individually, which is a great way to operate, particularly in wartime. And at least a lot of time. I mean, there's a time and place for large cabinet meetings, but there are also times when you need to get stuff done. And that's more efficiently done with one or two. So I think that, so he used to write, part of making money was going on tour and giving lectures. And certainly did some really interesting things in the Boer War and, India, you name it. But anyway, he wrote this article in 1931. He's like me. He kind of modified the thing again and again. He even kind of changed the title. But he actually described fusion power. Can you imagine anyone writing about this? Never mind really somebody in the arts, if you like, about fusion power in 1931, unless you have friends who are physicists, talking about fusion power. It was long before there was any practical means of doing this, meaning combining two hydrogen nuclei, two protons, to simplify it, to create one helium nucleus, two protons, so two protons together, and the release of an enormous amount of energy. So I thought that was really interesting. That would have come out of this conversations. And as I mentioned, I think last week, he went on sick children doing pediatric neurology. There was a neurologist there, and Stovall Pritchard. Stovall rarely went to the library. Stovall would go to talk to people. He'd find out, gee, this guy knows about this. I'm going to talk to him. So he invited him down to his place for the weekend and pump him for stuff. He'd credit the stuff. The credits went into the books and that kind of thing. He did the right thing as a scholar, but he didn't use primary sources. And I think that's a very interesting thing. So, but I think this is very interesting. The science-friendly environment that he created in the UK through government funding of laboratories, telescopes, and technological development spawned post-war discoveries in genetics. Well, think Watson and Crick, and of course X-ray crystallography was absolutely key to that discovery. And then he wrote this essay in 1939 titled, "Are We Alone in the Universe?" Now, skip all the stuff at the top. I think the gist of this is, he finished, I for one, now this would be writing 1939, right? And more or less the same view post-war. He finished with, I for one am not so immensely impressed by the success we are making of our civilization. Well, this is the guy who knows the First World War intimately, the lead up to the First World War, the interim years. He saw Hitler coming, and events in Japan, and what was happening in Soviet Russia, and in Italy. This is a realist, and about humans. We are making of our civilization here, that I am prepared to think we are the only spot in this immense universe which contains living, thinking creatures, or that we are the highest type of mental and physical development which has ever appeared in the vast compass of space and time. He's a beautiful writer, of course, and got a Nobel Prize for that. But it's really unusual. That kind of broad brush stroke with good support from members, people he knew in the science community. He wasn't a hands-on, but you know, in a way, he's like a theoretical physicist, or his friends, his best friends are theoretical physicists. I think that's a very interesting thing, and I happen to be very sympathetic to that view. Well, I'm not going to go there. I'm going to talk about a little bit about the brain that enables us to write, create stories, and transmit them to, or share them with others. And you've seen this slide in different things. It's interesting that some species of wasp, with only a few thousand neurons, are able to apparently do some version of facial recognition and differentiate one specific wasp from another in the group. That's pretty incredible. I think it's pretty incredible that you can cram 5,000 nerve cells into something as small as a wasp brain. That in itself is pretty impressive. Look at the housefly. 350,000 in a housefly. Those things I swat all the time. Over 300,000 nerve cells that I'm crushing with my swatter. By the way, the house cat comes out better than dogs. So I see dogs being led around all the time, but you never see a cat being led anywhere. Maybe that's why. Well, so when did an animal, it's an interesting mind thought to have. When did an animal actually look up sometime at the sky and wonder, what the hell's going on up there? And make sense. When did they think about death, their own death? Sometime something was going to happen to them and they would die. Maybe not right now, maybe a few months from now, or maybe a few years from now. When did that? When they lost a friend or a partner or whatever, what did they think was going to happen to them? What was going to come? When did that intrude, come into human consciousness? When did that come? And I think that came, it certainly didn't occur with bipedal apes. Not in this. These are all chimpanzee brain-sized Australopiths. Now I'm going to just try, there's a blank here. What would be your take on that skull? What would you take if you were Sherlock Holmes and looking at the skull? What do you think you could infer about the underlying brain just from looking at the skull? And you don't have to speak up or say anything, but if you want to have a grab, that'd be all right too. But what do you see? We see large orbits, for one thing. So in an animal with an ape here, with probably a relatively small cranium, maybe in the several hundred cc's category, a little larger than a chimpanzee. But there's a lot of, these eyes are big, and the visual system must be very important. But look at the forehead. It's almost sloping way back, so the frontal lobe isn't well developed. here. It's not well developed even in a small brain, relatively small brain. This whole area here, this flat side, tells you something about what they were eating, because the muscles, the jaw muscles, insert on. You can feel your own, just try biting and feeling up here. You feel the temporalis muscle and the masseter muscle contract here. They're very powerful muscles for chewing. And you need big, strong muscles like that to chew legumes, that kind of thing, not for fruit. And so it tells you something about the diet, tells you something about your resource allocation in the brain, however, whatever its size. Now, here's this book, by the way, is a favorite of mine, John Gertie. John Gertie works in upstate New York, but he creates a lot of the recreations of what these animals would look like for the Smithsonian and other museums in the world. It's a great book. And by the way, he ends in his last chapter in a really interesting speculation about what's going to happen to us as a species. But one of the interesting things is, look at what he says that he spent a lot of his time looking into the eyes of the creatures he develops, and he often wonders, well, what are you capable of thinking? And never more so, when does the skull come alive? When he puts the eyes in. And that's when they come alive. And interestingly enough, facial recognition programs, the eyes are much more important than certainly the ears, the nose, the mouth. It's the eyes. And artists will often say, portrait artists, get the eyes right and you'll be forgiven. Some of us get the eyes wrong, the whole damn thing's worthless. And there's some truth in that, I think. But look, it really looks like, doesn't look as if, it just looks curious, doesn't it? Doesn't look fearful. And by the way, these are white sclera. In our early ancestors in Africa, the sclera, the chimpanzees and bonobos, would be brown. The sclera would be brown. And people could spot that. So if you want to hide, you're better to have darker sclera. And and keep going here. Now here's one that's a very issue, because this is Lucy's species, Afarensis here. These are the Prince in Tanzania, or could be Kenya here. Very interesting. Here's an adult walking along here, straight line, at a leisurely pace, and look at the smaller prints of a child along the side. So there's an adult, a child, bipedally walking along, good balance. Now look at the foot. The foot, their foot, looks like our hand. We have an opposable thumb. That's that precision grip, the thumb and the index finger and the other fingers. That's a really special acquisition. That allows us to knit, garden, and be an artist, and draw and paint, and work with tools. That precision grip, which is so important. They use that precision grip to clamber up trees. Wrap the thumb around, with the digits around, clamber up trees, and it's lost in later, in another couple of 100,000 years, and that's gone. Versus, well, that would be what our foot would look like. But isn't that interesting? The thumb, or at least the big toe, is really quite separate from the other toes. That would be like our hand. And I think that's a really interesting thing. So now we're getting to our story a little closer, and that really begins somewhere around 1.5 to 2.5 100,000 years, but No, what is it, early Homo erectus here. These are transitional species, of which I only included one, Homo habilis, the tool maker, so to speak. The brain size has gone up a couple of hundred cc's here. These would all be bipedal. Homo erectus is kind of the screw up. Somebody's got to do something about this, because this species subsumes under it quite a variation, because these were out of Africa before humans were out of Africa, and long before Neanderthals and Denisovans. Erectus, or whatever erectus became, dispersed throughout Eurasia, ended up in Indonesia, and kind of died out a few 100,000 years ago. So they had a long tenure. They lasted a long time, longer than we'll probably last as a species. But in that period of time, subsumed under the same name, their brain almost doubled in size. I find it a little hard to believe that that's the same species. It obviously has moved along cognitively and in size, and certainly the size of the brain. But I think somewhere in here, somewhere in this period in here, maybe as far back as maybe 500,000 years, some people say 700,000 years, to the roots of when one branch headed off to what would become us, and another branch headed off to what would become Neanderthals and Denisovans, and species yet to be found. That kind of began around 600, 700,000 years ago, that divergence. There's a lot we don't know. I mean, this fossil record is very partial, but it's certainly become richer in the last, say, 20 years. Anatomically modern humans, meaning the skull that looks like us. Well, what is something like us? Well, here we are. This is actually a nice one to look at. This is early Neanderthal, so this could be Spain, and a late Neanderthal within 20 or 30,000 years of their extinction, I should say. Maybe they were distinguished, but they went extinct. The Moroccan skull, that some people consider to be the earliest sapiens, I disagree, and sapiens over here. Well, what do you see? Well, I'll just walk around here. What do you see? Well, let's just start with the human one. Humans have a very globular skull. It's very different, and they have a very vertical forehead here. That's what distinguishes modern humans from the other variants. And a species that behaves like us, with our imagination, our creativity, our language skills. And this Moroccan skull, you can see the forehead is still receding, but it's not globular, it's really much more longitudinal. It's very closer to the Neanderthal. So somewhere in between. These species, of course, these names, as I mentioned before in other talks, these are created by fossil people to separate people, different species out, depending on their skeletal features and the shape of their skull, but also their spine and various joints, the pelvis and the hips and the knees and the shape of the hand, etc., the shoulder. So, but they're like forming planets. All of those different muscular or skeletal features didn't come as a package. They were created first. There might have been the pelvis kind of changed, and if the pelvis changed, then the hip joint had to change, and the knee joint had to change, and the ankle had to change. But other features, and then the shoulder would change with the use of the upper limb. If you're not clambering up trees, you don't need something to go around a thing or to hobble along like this. You want maximum mobility. That's why the shoulder joint is so shallow and so easy to dislocate in humans. And anyway, I thought you should see that as a progression. You don't need that. Now, this is something I've talked about in 2 or 3 series, but it's kind of taking off now, these mini-brains. Well, there they are, a bunch of them. And these are these little mini-brains in a petri dish. So they're, look at the thumb size and the finger size, so they're pretty small, right? How did they get there? They started out with, in the case of us, humans, getting a sample of skin, might be fibroblasts or some other cell, and tweaking it such that it reversed course and became a stem cell. So it had the potential to become any human cell. And then they redirected it to become the brain. It's not as hard as you think to do this. It sounds very astounding when I say it, but it isn't that hard to do. And here's one of them. By the way, this the fluorescent cells here. These are cells fairly early. They're kind of multiplying. They're beginning to organize themselves. But this tiny little blob would be 0.5 millimeter in size, not the 5 or 10 millimeters it's going to become. And then here, you can stain them. And you can begin to recognize that there are different subgroups here. And that's what happens with us. I mean, we start out with one kind of cell, one type of cell. It differentiates into, and keeps differentiating out like a branching tree into different cells, hundreds of different cells, thousands of different cells, each with their kind of target zone, the place where they're going to live, and they're guided there by molecular signals. It's an extraordinary process under genetic control. And and if you keep going, you get this kind of, now this is a simplified version, but I've showed you this slide before, but it shows you the structure of the cortex in mouse, Neanderthal, and modern human. Three examples. What's interesting is that there is a structure, and it's a very similar structure. I mean, the mouse has a very similar structure to us, just not as complex. And Neanderthal neocortex, very, very similar to us, but not quite. And this business, when Neanderthals were first discovered, because of their kind of brutish appearance, people assumed that they were dim-witted and kind of stupid and certainly didn't belong with us. Well, we since know that's not true. We know that they created cave art thousands of years before we did, or at least there's any record that we created it. And that they created flutes, sets of music, probably had symbolic language of some sort. But no Neanderthal ever created anything like the cave art produced by humans in Indonesia and in Europe. So there clearly is a cognitive difference between the species. And it shows up in the structure of the neocortex. I put this in, it really doesn't belong in here, but I think, given the audience, you might be very interested in this. They've looked at MRIs of 120,000 people of various ages. This is a log curve down here. So this is 0, this is birth, 1 year, 10 years in here, 100 years down here. Now, the most important thing to look at here is this blue, this dark blue one. Sorry, not the ventricular volume, that's here. But this one, cortical thickness, the neocortex. We're not talking about basal ganglia here, we're talking about the neocortex. Look at this. Within, in utero, before birth, the neocortex is very well developed before birth and kind of peaks in late infancy. Not at 5, not at 10, not at 15, not at 20, and it's starting to fall off, and they're still in childhood. That's the neocortical side. And if you include kind of deep ganglia, other gray matter, then the curve is kind of a little bit more to the side. This is gray matter volume here. So it's a little bit more or less the same. The peak here is around 12. You know, this fits very well with one of my working hypotheses that the motor skills that we have, that children learn really easily to ski, to dance, to do almost anything really early. And you know, at the age of 3, 5, 5 to 10, 15, that's when the speed is there, that's when the coordination is there, that's when it's at its peak. And yes, we remain very skilled from a motor point of view right into our 20s and 30s, but there aren't many world Olympic gold medal winners and the 100-meter, well, none, in the 100-meter dash past 30, and the 200-meter dash. Long events that require endurance, older people gut it out, and they can do well into their kind of later time. But the point I'm making, these mirror one another. The learning capacity of the brain doesn't know this is a motor task you're learning, or you're learning to do language here, or you're doing whatever you're doing. The brain, if you look at different regions of the brain, they don't look all that different. I'm talking about the neocortex. They do. There are differences, but not a lot. It's the same brain doing a lot of the stuff, and I think there's a sweet spot, and the sweet spot for acquiring new stuff, particularly mathematics, or I would say theoretical physics in the earlier days, when you didn't take 20 years to mature and get your PhD and do all that kind of stuff before you set about doing your really creative stuff. But you can do this kind of stuff, you can acquire it quite early, if it doesn't require a huge body of knowledge to be acquired. So I think it's very similar. Now, where does this fit into Neanderthals and modern humans? Well, I was listening to a theological piece the other day, and pointing out that Jesus, for example, at the age of 30, was already an old man within his community. In other words, people didn't live into their 40s or 50s in those days. It's certainly true in archaic humans, and 100, 200,000 years ago for modern human fossils. You're not looking at old fossils. Well, they are old fossils, but you're not looking at an old skeleton. You're looking, from our perspective, to compare it with us, people up to the age of 20 to 30. So, and well within that sweet spot for kind of learning, but not later. I think this is a really interesting slide to put together. Now, this is summarizing a much more complex constellation of data here, but I thought you might be interested in seeing that. Now, here's the art. There's a common ancestor for this kind of art, because figurative art exists in the Far East. This is in Indonesia, 44,000 years ago. Notice what the artist does here. First of all, the hunters are very much smaller than the prey. That's something that happens in the cave art. There aren't many humans in the cave art, and they tend to be stick figures. Furthermore, they have a bird head. Probably not literally a bird head, but a headdress. And there's one of them, two of them, three of them, four of them here. Maybe another one in here. So it's a scene. It's a hunting scene. And And then here we are, probably 20,000 years ago. Isn't this incredible? It's Picasso, who lived in Spain for much of his life and visited many of these sites. But he was quoted one time as saying, "We have nothing to teach them." And what he meant was compositionally speaking. They got it. They had a sense of movement, and there is a sense of movement here, isn't there? These are lions here, and they're moving. You can see, even though they're separate heads, they're moving. It's kind of a trick. Remember the early movies where they've just kind of frame by frame, and it's in a way people suggest that that's what they're trying to do. The other thing is, of course, these are in the light of this is a uniform light, but the light here would have been flickering, and that would have added enormously to the sense of mystery of what was going on, and much of what was around you wouldn't have been lit. You couldn't see it. So it's really quite extraordinary, the art. Now, so the brain was clearly beginning around 40, for modern humans, beginning around mid to 40,000 years ago, 40 to 45 to 40,000 years ago, clearly had the capacity to think this, to imagine it, to create it. This took time. This wasn't something this isn't somebody's doodle. And these days you can go on the net and do virtual tours. They're really interesting things to do. For some reason I couldn't do that here today, but I'm going to try. These virtual tours of Schmidt, and they take you in one cave into another through these very tight passages. You wonder how the artist ever squeezed himself through that passage to get to the next, and even stopped in these tight spots to paint or make images on the walls. It must have been very potent. And Richard Leakey wrote, for me anyway, a very moving account of what he thought was happening, what he imagined was happening in the cave. Now, it wasn't an uninformed one. After all, he lived in Africa all of his life. He certainly knew Shaw men and was very familiar with them. There were gatherer-hunter societies around him in Africa. He understood that. Doesn't mean that these were hunter-gatherers in the same way that you could substitute modern versions for them. We don't know that. They didn't leave any script, so we don't know. The amazing thing, I think, of these caves are as cathedrals. It's a good way to think about them. And one of the things about that is the respect. You know, people visited these caves many times, and I'm not talking about next year, I'm talking 5,000 years later, or 10,000 years later. No one erased anything. No one went in and said, oh no, they got it wrong, and did something on top of it. That's an interesting thing. I think that's a really interesting thing. So, and well, there's Picasso, so we would have been right at home. I think different materials, a lot more opportunities, art schools, etc. But anyway, here's that. Imagine the level of imagination here to create this. Something, a statuette, that has the head of a lion and the body of a man, of a human. Is that a little like that image I showed you in Indonesia? It is. What does that suggest to you? That there was a common origin for this art. That somewhere the artists, what would become the artists, maybe thousands of years later, of the cave art in Europe, shared a heritage with those that headed east into Indonesia and elsewhere and created art there in a very similar way. So common ancestor, that's what it's telling us. And Neanderthals created, you don't see it here, but a four-hole flutes. And actually you can play these things, or people have played them, made models of them, and they create lovely music. And and the right hands or the right mouth. And this goes back 60,000 years ago. Have a sense of rhythm and music and understand maybe not the physics of it, but the importance of the distance between the holes and creating the notes. And must have taken a lot of playing around time. And this is an early human flute. Some of them are much more complex, but going back 43,000 years ago. Now, it's a nice one. Footprints. This is all about perspective and storytelling. This is northwestern Saudi Arabia. At a time when satellites show multiple lakes in this area. Well, it's arid now. It's desert now. So this was an interglacial period. It lush plants, animals around. It was easy to disperse out of Africa, or, as some would say, two-way traffic from Asia into Africa. We always think it's out of Africa, but it's into Africa as well, and within Africa. Africa is a huge continent. There are a lot of migrations taking place in Africa. So this is a modern human with footprint along the shore. And there's Apollo. What is that? Apollo 11. Those prints would be still there, right? Absolutely still there. And we haven't landed on Mars yet, but we will in maybe the next 2 decades. So that shaping, I don't know where we're at our time, going well past my time. So I'm going to take an opportunity the next time to actually read you part of this, because he's a good writer. Strong Gertrude. Yes, he creates these incredible representations of what different species look like, but he's also a very imaginative person. And I don't want to ruin this story, because in a way it's the ultimate creation story that he's managed to put together. And so we'll leave that for next week. So next week we will do the black holes, because I do have to do it, get it out of the way. Then we get into some more interesting stuff after that. Any thoughts? No? Silent?
Might be, I'm not sure if you've already answered this. So when did the frontal cortex start to develop in humans?
Oh, I probably, this is phrenology. We're talking about the shape of the skull, and therefore the shape of the interior of the skull, the endocast. But for a brain that looks like ours, that goes back to at least 190 to 210,000 years ago. Now, people are always finding fossils, but unfortunately the heyday has been very badly disrupted. I mean, fossil-rich Northeast Africa has changed so much that it's not like Blicky's days, where you can go out and find the stuff very easily. Now, there are private tracts, there's farming in the area, and a lot of potential sites have been destroyed, so we may never know when that threshold was passed. I think the behavioral threshold probably corresponds well to the anatomical one. And so it would go back 200,000 years, and might go back further. And we don't have to assume. I mean, somebody didn't go from, it's not like a Porsche going from 0 to 100 in 2 seconds. Stuff like this would have taken a long time to evolve behaviorally. And there is that marvelous poem, The First Geniuses, written by Billy Collins, which I want to read, or get one of you to read one of the sessions, but it raises this question. You could be, he poses, well, he doesn't use this model, but it's the idea. If you had 5 Albert Einsteins sitting around, say 200,000 years ago, what would they talk about? Would have anything to talk about other than the weather and who caught what or did what? I mean, the content of conversation and the thinking, it really depends. In those days, he would have been, he would have had a very intimate knowledge of the land and what they needed to do for shelter and for food and providing for his relations and family, that kind of thing. And they had would have had the advantage of communication with one another. But even then, the groups would have been small, maybe max 100. Overnight group might have been 30 to 60. So who do you actually talk to? It's the same group. It's like living in some tiny, tiny version of Niagara on the Lake or Virgil and constantly seeing the same people and hardly anyone else except migrants that might go by, or maybe you trade with a group that's 50 kilometers away. And so the body of people you can learn from, or if you had some great insight, who to share it with? That's the question that Billy Collins raises. If you had a great idea, who would you share it with? I mean, when Einstein came out with that quantum theory of light, there was a group to talk to. There was a literature. Yes, he didn't do any of the experimental work for sure, but he was aware of the questions that the experimental work had posed, and then he came up with a solution. That's a special kind of intellect, I think. But I think sometimes Brenner, who won the Nobel Prize for discovery of RNA, he was born, I think, if I've got this right, his family was born in Poland, and he, I think his father was a cobbler, and his mother did washing for other people. They got out of Poland because they were concerned, I guess, with the World War I and in the wake of World War I, and maybe saw the tea leaves, and moved to South Africa. Their son, believe it or not, got into medical school at 15. And 3 years later, he was in Oxford. And within that year, he met Watson Crick. So getting back to that slide of the kid, I think young brains are really capable, and if they don't have much opportunity, and I don't know what his fate would have been if he'd stayed in Poland, but he was lucky enough with scholarships and people around him to kind of see that, hey, this kid has promise. Then how many people out there, I would guess they vastly outnumber the number who do have the opportunity. There are a lot of really capable people out there, but we don't know them. And we wouldn't recognize them from the language that they use when they talk to us, because there's a certain class used to language. It affects things. I mean, somebody used to hear this sometimes at Oxford, that they could tell exactly where you were from, and maybe something about your past and your prospects from your accent. And I think those days are coming to an end, but they certainly ruled the roost for a long time. And so I think that there are really capable kids. I'm just amazed that you must, just looking around the group here, we're talking about grandchildren, children and grandchildren, except maybe you, but children and grandchildren, and especially maybe grandchildren, and being amazed at, wow, you're doing that now? So I think there are many more people capable than we know about. There are a lot of Einsteins around, potential Einsteins, and many more than the actual count. You know that Camelot period in physics that I did one on it from 1900 to 1930. That was an amazing period in science. It lasted maybe to 1940, but I got 1930. But in that period, a whole new field, quantum mechanics, was developed. And if that wasn't enough, we find out in the same period that there was likely a Big Bang, that the universe was changing, and general relativity is published in 1915-16. Not all of the implications of which Einstein was aware of himself until others who read those equations looked at them and said, hey, did you realize this? Next week we'll talk about this because black holes. Schwarzschild was a member of the German army serving in Russia, and he was an officer in the artillery corps. So, but he was a physicist and a mathematician, a very good mathematician, and he followed the literature. And he read Einstein's general relativity paper, as few could in those days, and make sense of it. And there was a very gentlemanly exchange of letters. And in that letter, Schwarzschild pointed out to Einstein, are you aware, looking at it, probably didn't put it that way, but when I looked at your equations, and I thought, what would happen if the mass was really large? My take on that is that space-time, as you talk about it, would collapse in on itself and create singularity, what's called a singularity. Well, what is a singularity? Well, it became a black hole many years later. It became the beginning of the universe, a singularity, when all matter, all energy, effectively everything becomes energy, condensed into a very, 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 very small space. And at the center of a black hole, or at the start of a universe. And Einstein was, he appreciated this, and he said, I agree with you, the equations suggest that, but I don't think it's likely. And I don't think it's likely to happen. Well, it does, and now we know that black holes are extraordinarily common. And, or the last one with Einstein was the one about gravitational waves. Again, somebody came to him and said, if two masses collide, or one explodes for some reason, there are going to be ripples like on a pond in space-time. Like the trampoline is going to bounce up and down. And it will travel at the speed of light, that signal, throughout the universe, and it should be detectable. Now, as it turns out, that great idea, Einstein again looked at it, and he was right. He said, well, they would be so faint, almost impossible to detect. True, until the 20 teens, when the Nobel Prize was awarded for it in 2017, and the first ripples of space-time were picked up in 2 years before that. But now, you see, that's the window. No telescope can see back, at least that deals with radiation, light, energy, can see any further back than about 4,000 or 400,000, 300,000 years after the Big Bang. Because the universe then was so incredibly hot that it was a plasma sea of ions, and nothing got in, and that's the way it was. And until the universe had cooled down to close to absolute zero, and actual atoms could form, electrons could bond with protons, and light escape. But gravitational waves, which almost certainly would have been created with a Big Bang event, they should be traceable right back to something much closer to the Big Bang. So that's what people are now looking at, this gang of, in Italy and in Japan and in the United States, and I've forgotten where in South America, developing this kind of technique for detecting these really, really faint signals, these little chirps. And that'll be maybe the best evidence for the Big Bang when that happens. So gravitational wave, well, he dismissed that one, and most famously, the one when Lemaitre, the priest, the Roman Catholic priest, who got a PhD from MIT, so he knew what he was talking about on the math and the physics of the time, looked at general relativity, met Einstein at MIT, and kind of closeted him and said, when I look at this stuff, your equations suggest that the universe is expanding. And it's expanding faster and faster. It's accelerating. And that's what prompted the response from Einstein that your mathematics is correct, but your physics is terrible. Meaning that not all mathematics, however well done and understood, is reality. True, but he missed a huge opportunity because if he had just listened to him and several others, there was another Nobel Prize for him. He would have been the father of the Big Bang. Instead, he introduced a cosmological equation into his equations for general relativity to restore a stable universe, which has an interesting wrinkle because it was a manipulation, and then when he had recant in the early 1930s, evidence from Hubble, and then so took out the cosmos. Well, in the 1990s, Peoples, Canadian, got a Nobel Prize for the mathematical modeling of the earliest universe, what happened actually, the Big Bang, and early on. And Peoples looked at it and theorized there had to be dark energy to be the engine of this expansion. There had to be. And it was the only way this thing actually worked and would be consistent with the data. Guess what is equal to the cosmological constant? Dark energy. The number, so Einstein was wrong twice. One, he put the cosmological constant in, then he took it out. And he didn't know, he died well before that, but isn't that refreshing for all of us that even the brightest among us make horrendous mistakes? I think that's a great comfort to me anyway. So next week, black holes. On we go.